Okay, guys. So the previous chapter, it was just a flavoring of the axiomatic approach. It's not particularly necessary. I mean, in other words, you can survive and understand the most interesting and important parts for this class without knowing that previous chapter, even though I would suggest that you know everything here. So I hope you also began reading either Kafka or The Gambler. Actually, would be happy if you read both. Pretty interesting book, The Castle. So here is where we left off. Sample spaces having equally likely outcomes. So a sample space is the collection of all possible universes, and each outcome is an actual universe that comes to be realized. And when we say that the sample space is having equally likely outcomes, we're claiming that there is no preference. There is the general indifference for what outcome will occur. Is it outcome 1, outcome 2, outcome 3, outcome n? And so they are assigned by the axiomatic approach, are assigned the same probability value, p. And what is that probability value, p? Well, we know by axiom 1 that the sample space must have probability equal to 1. I think it's axiom 1, but one of them, right? And then we already proved that finite or infinite union of disjoint outcomes or disjoint events creates additivity in the function. So it's the probability that 1 happens is probability that outcome 1 happens, or outcome 2, or outcome 3. In general, it's this sum, probability that outcome k happens, and all of them are p. I hope it's clear, p plus p plus p. So it's p repeated n times, and that tells you that the probability of each individual outcome is 1 divided by the number of outcomes. Okay, just like some people remember about the coin, you said, why is the probability 1/2? You said because the event where head comes up is 1 universe out of 2 possible universes, right? So that's what people said. It's correct to reason this way if each universe is equally likely to actually come into existence. So this probability is 1 divided by n as follows. I hope it's clear, guys. And if not, it's very important ideas. Even if they sound simple, they are not simple at all. So that means that the probability that E happens is just the number of outcomes in E divided by the number of outcomes in S, assuming, of course, that S is a discrete universe. All right. And so if 2 dice are rolled, what is the probability that sum of upturned faces is 7? So we solved that before, right? So we consider 2 dice are rolled. This is a very poor universe, having only the outcomes are what the dice are showing. So the dice can show 1 and 1, 1 and 2, 1 and 3. There, in general, there are going to be 36 possible universes here. And we can see that because we know what is our sample space, right? Our sample space can be represented with with what I call Kafka protocol, consisting of 2 boxes. And each box will be a number between 1 and 6, right? So kj, so you see that why I know the number is 36 is because here I have 6 possibilities times 6 possibilities, it's 36 possibilities. And now how many of those possibilities correspond to the sum equal to 7? Well, all we have to know is what's the value. So what's the value on the first die? If the value is k, the value on the second die has to be 7 minus k, correct? So as soon as I tell you what this is, the other value has to be determined. So that means that there are exactly 6 possibilities that correspond, 6 universes that will correspond to sum equal to 7. 6 divided by 6 squared is 1/6. So before I continue, guys, everything clear so far, what I did and what I accomplished using the Kafka protocol? And you don't always have to write it so precisely as I do, but it would be nice on the exam if you, especially for the more complicated questions, if you give me an indication of what you did, what calculation, how you carried out the calculation. And one way will be to do that using what I'm showing you here. You can do it with not as pretty notation. Good. So all you have to do is, what is chapter 2? It's doing combinatorial arguments twice, once for the numerator and once for the denominator, and you just have to decide that how do you count the same thing. They say you're counting the same type of universes for the denominator as you do for the numerator. They are of the same type. Okay. So again, right? What's the word random? Just to remind you, we're going to use the word random, and random you can take it to be the synonym of indifferent. A random outcome means that there was no preference for this outcome. This outcome was just as likely to occur as any other outcome in your sample space. And here is that problem. We did solve it, but let's do it again, guys. And I cannot see what you're writing. Unfortunately, I cannot go between your rows, but I would have liked to see a protocol. I want you to imagine it as clearly as you possibly can. So we have 3 balls. They are randomly drawn from a ball containing 6 white and 5 black balls. What is the probability that one ball is white and the other 2 are black? Once you're ready, type your answer in the comment or speak if you prefer to speak. So my announcement was that we do not have calculus. I think you did not read it. It was specifically that we do not have calculus, but we have probability today. It's a Monday schedule. No worries. Calculus, Alan, will happen on Thursday. And guys, so Bowen, you see, you are writing multiplication of probability. That's fine. We will develop so many other techniques, but I want you to reason using the techniques that we developed. It's important, right? It has to be extremely precise how you think of it, right? Why do you multiply probabilities? That might not be right. let me know when you're ready. Chabeli. Today we have two rabbits here, I think. So Alejandro, what you're calculating is numerator, right? And then you need to do also the denominator. So even though, guys, this is relatively a simple problem, we will go through a very thorough analysis, right? It's a very thorough analysis. All right, so let's do that, guys. Okay, Sandy. Very good, Alejandro. All right, so here, let's go through the solution, right? So again, I want to emphasize it's a combinatorial problem for both numerator and denominator that you're solving here, yes? So it's like twice a problem from chapter 1. So, and also there are also some assumptions that that we're making here when we solve this problem. So Alejandro, when you solve this problem, you made an assumption, and who else? On the other person that solved it also made an assumption. So here is how I think of it very, very precisely. So first assumption is, let's assume that every single ball is distinguishable. And balls are drawn in order, okay? Now, in a properly regulated society, you have IDs. You must carry IDs all the time. So let's say that we have those are the balls. We have 6 white balls and we have 5 black balls, yes? So each ball is given 2 IDs, the population ID, which is just its rank 1 through 11, and its color ID, which are the numbers that I wrote below. So it has 2 IDs. So for example, white ball 1, its color number is 1, and black ball 7, its color number is 1. Okay, I use that to make my documents precise here. Okay, so this is what I know. So then I can construct a Kafka protocol for how to process this information. So here is my event. One ball is white and 2 balls are black. Yes. So here is how I do that, guys. You see. So you look at that, right? So this is my first way of counting it. So I have this document. I have place of white ball number. You see the white number. So the white ball number comes in and it shows that it has a white ID. And then that white ID will be recorded in this box. And then here we recall the black IDs, the other 2 balls, right? So here is an example. Suppose that the actual outcome that came out, and I know here, I want to show that here I'm assuming that I know the order in which the balls were selected, right? So that means that black ball number 9 was first selected, then white ball number 3, and then black ball number 7 was selected. How do I put it in this document? Look at it, place of white ball. This white ball appeared as the second, so I put 2 here. You see that? I'm just trying to show you how I think in codes, right? So second, it came to. Then I record its color number. That's the white color number 3. So I know the ball because I know that this is a white ball and that's its color number. And then I put 3 and then 1 because black ball colored 3 and colored ball number 1 came in this order. That you see, reading this code, I can reconstruct the pattern, and looking at the pattern, I can put in a code. Do you see that? Do you agree that that can be done? Yes, guys? Yes?
This looks a little bit complicated.
It is a little bit complicated because it is bureaucratic, and bureaucracy is always a bit complicated. That's why you have to read Kafka, right? That's why I call it Kafka protocol. But reasoning this way will eliminate all errors. So I can do it fast. You see what I do here, I can do in a second, but I also think very precisely. Understand? I think exactly what am I counting. If you do not know what objects you are counting, then you are going to make mistakes. And it's very funny to me because in all of it, you understand, I have very dark sense of humor, and I put my sick sense of humor right into my paper. So here, you see this? So let's count how many outcomes are in E. Well, first of all, how many possibilities for positions? There are 3 possibilities for position, yes? There are 6 possibilities for the white number. And here we have 6 possibilities, five possibilities for black number, and another 4 possibilities for the next black number. Good. So the answer is 3 times 6 times 5 times 4, which for important purposes I will put like this, like what Alejandro solved it. I said. So Alejandro says, well, 6 choose 1 and 5 choose 2. So this is the black ball chosen, the white ball chosen, and 2 black balls. And then there are 3 factorial ways of putting them in order. So that will end up being the same. Good. And so what is my Kafka document for the full sample space? My Kafka document for the full sample space can be just first, second, and third ball. And I just use the population number here. So there are 11 population numbers that can be first. Once that happened, there are only 10 left for the second and 9 left for the last. So the probability for E is the number in E divided by number in S, which is what I calculated divided by the combinatorial argument for the denominator. It's 4 over 10, which is also the same thing as 3 factorial 6 choose 1, 5 choose 2 divided by 3 factorial 11 choose 3, which happens to be 6 choose 1, 5 choose 2 divided by 11 over 3. Good. You have to understand, guys. So of course, some of you, especially if you're somewhat comfortable, you can solve it much faster. I'm trying to teach you a procedure that if you follow it, you will avoid mistakes. So whenever you count something, you have to visualize it as precisely as you possibly can, and then no mistakes will appear. And the problems become very simple. You learn to think this way, right? Once you go to the castle, that's exactly how you think. Assumptions number 2. Assumption number 2 is that all balls are still distinguishable, but we no longer know which ball came first and which second. So they were sampled simultaneously. You understand? So before I assumed first, second, third. So I know, so if it's a lottery, I see the first ball coming out, second, third. Now I'm assuming that they are picked simultaneously. So what is the Kafka document for my desired outcome E, for the event E? So then I think of it this way. The white number and the 2 black numbers in order, which I see I don't have a full line here. I indicate by a dash that here I put a number in order. So for example, if the selected numbers were 9, 3, and 7, I will put the white number here, and I will put the black numbers in order from lowest ranked black number to the next black number. Good. So the Kafka form for the denominator will be just select any of the, select just any particular balls by their population, and that will be just put in order. So if the selection happened to be what I drew over here, 6, 10, and 5, I will put 5, 6, and 10. So how many possibilities are there for the first position? It's 6 choose 1 possibilities. Do you agree? Because I choose one of 6 numbers to be the white ball, and here I have 5 choose 2. I choose 2 numbers for the black ball. Right. So when you solve those questions on my exam, I would extremely appreciate if you put it in either this form or something equivalent, so I right away know how you carried out your calculation. So I look at your calculation. If it's correct, it's very easy. But if it's incorrect, I have to start guessing what went in your mind. How close to correct is it? So to make that easier for me, I want you, and also to improve your imagination, I want you to write a Kafka form. Doesn't have to be as pretty as what I do, but you understand, it should be a form so it's clear exactly how you were thinking. It has to be precise bureaucratic thinking. Can't emphasize that enough. Now, you observe that both assumptions led to the same result. Look at it, 4 divided by 11. Which of those procedures do you think was easier, computationally easier? Computationally easier was which procedure? What do you think?
Second one.
I think so, right? At least, of course, it depends on how you carried it out. Of course, if I carried it out, I mean, I could have done it this way. Maybe that's simple, right? But I specifically wrote 3 factorial over 3 factorial here, right? So there were 3 factorials that ended up not being important at all. Good. So here is an observation that that I would like to make you notice. So sequential random sampling generates the same probabilities as simultaneous random sampling. You've seen before we made 2 assumptions. One of them that sampling was simultaneous, the other that the sampling was one at a time. They generate the same type of randomness. Let's see why that's the case. So let's suppose that we have a population of n balls, and out of those n balls, we want to select some collection R. Okay, some collection R. So let's say the outcome will be a success if this particular selection of R will be given to us. They are, let's say, I give them secondary numbers 1 through R, so that I can distinguish them from the rest of the population. You understand? Basically, I want to know if what's the probability of selecting a specific collection of balls, and to speak of all of them in general, I would make the particular selection of balls. I give them extra number, the red number 1, 2, and R. So in this case, I just picked 3 to be red 1, 4 to be red 2, and so on. Good. But the idea is I have a bunch of balls. There are n of them. I want to prove that that the probability of selecting a particular collection of R balls is the same if I do the sampling sequentially, or if I sample simultaneously, or ignore that sequential sampling has happened, right? So what's the probability of simultaneous sampling? Well, that's very simple. In simultaneous sampling, we are assuming that all choices, all n sub R choices are equally likely, right? So there are n sub R choice, n choose R selections of balls, right? And all of them are likely. There is only one of those selections that corresponds to 1, 2, and R. Are you with me, guys? So you talk to me so I know you are with me. And yes, so it's easy to get lost here. Now, if you are with me, what would be the difference? What happens if I make a sequential selection, right? Sequential selection means that all R factorial times n choose R possibilities are equally likely. You agree why there are factorial? Because the R factorial here tells me who was first, who was second, who was third, and so on. So denominator means we know the sequence in which those balls came out. And then selecting 1 through R has R factorial possibilities, right? So because maybe number 2 came first and number 1 came second and onwards, right? So that would be R factorial possibilities in which those particular balls could have come out. And then the R factorial crosses out and we have P sim. Now you see, we did not calculate the same universes. They are not the same sample spaces. The reason we got the same answer is that a different number on the numerator divided by the number in the denominator can equal to the same fraction. You see, in probability, you have some flexibility in picking up the sample space that you find most convenient for calculation. It's basically for the same reason as, let's say, 2 divided by 6 is the same as 1 divided by 3. Understand? So you can, each of you can pick a different pair of combinatorial problems to solve, and the solution still ends up being the same. It's slightly more flexible than what you had in chapter 1, and sometimes that flexibility is very useful. All right, so let's consider this. That you can pick different sample spaces. Yes, there are infinitely many sample spaces that you can select, but you always, here is what you have to remember, guys. Okay, David, I think I sent an email again, right? That today's Tuesday schedule. That's why I sent it. I expected lots of people to come here, right? It's Tuesday. You should all practice the art of reading letters, right? And not just or clicking and closing it. Today is Monday schedule. The next class is on Thursday. Okay. So now we solve this problem, guys. A committee, oh, before I go to the problem, one thing. Don't forget this, guys. So as soon as you pick your sample space, make sure that what you calculate in the denominator are the number of outcomes in that specific sample space. And what you calculate in the numerator must be the number of outcomes in that same space. If you select one sample space and then implicitly calculate outcomes for the numerator that are from a different sample space, you will be wrong. You understand? It has to be, you must imagine the universe, the universe of all universes with which you're dealing. What are the outcomes? And then count the relevant outcomes from that universe. If you selected implicitly 2 distinct sample spaces, you will produce an incorrect ratio. Let's try this problem. A committee has a committee of size 5 must be selected from a group of 6 men and 9 women. If selection is made randomly, what is the probability that 3 men and 2 women will be serving on this committee? Go ahead, calculate. You can decide which sample space to pick. Okay, Bowen, you are absolutely correct. That's a possible sample space. But here you assume that sampling was simultaneous. It's a great disadvantage that I cannot see what you're writing. I want to see Kafka form of sorts. Yes, simultaneous. That's what I tried to prove in the previous in the remark. So sampling. You see, how do you form the committee? You can form the committee by deciding to pick the 5 individuals one after the other, or I pick them at the same time somehow. So how do you imagine picking, right? So imagine it's like you have this device, the machine, and it's grabbing the individuals like kegs one after the other. That's consecutive or sequential sampling. Can you imagine that? And then imagine that you have this machine with having 5 arms, and they reach out and grab the member of the population. Okay, that's a different sample space. One of them is, the other one is. I always want Kafka, guys. It's a good book to read. And again, The Gambler and Kafka. Yes? You see, extra credit possibly, but then I don't, you see, I have trouble believing people that they read now, right? They just find Spark Notes or something better than Spark Notes. It really pisses me off. And even to actually give extra credit for something that you should enjoy doing, it also annoys me, right? You should be driven to it, like flies to the fire.
How big are the books? Like, do you know the page numbers? Like estimates?
How big it is? Well, Das Schloss, or The Castle by Kafka, it's unfinished. But Gambler is very short. Dostoevsky's books are usually pretty big. Gambler is very short.
Well, it's not that short.
Oh,
compared to Crime and Punishment, it's short, but it's 200 pages. It's 200 pages.
It's definitely longer than my email, and as you can see, not everybody reads it.
200 pages is doable. That's not too bad.
But also, you were asking us to enjoy Dostoevsky. I hate Dostoevsky.
Well, that's because
I was forced to read him. Yeah, I was forced to read him.
Well, you see, you're even trying to hide your accent, right? No, you have to show me that. No, you cannot hate Dostoevsky. You just took it in school, and that usually happens. Everything that I took in school, I hated it, right? I also once drank a full bottle of Coca-Cola, like 2 liters, right? Then I hated it for half a year, but I drink Coca-Cola instead of water all the time. Good. So let's. I'm sorry for interrupting you guys. And we can discuss, guys. We can discuss Dostoevsky. We can discuss Chekhov, right? It's all one of my schemes. Okay, Nomi, so based on the fact that you said 5 factorial, I presume that you sampled sequentially. Okay, let's solve it together, okay? So those are simple problems. You might again be annoyed by the full procedure that I do, but trust me, right? I had similar problems that you will be having in probability, and I developed my technique to avoid those problems. And I do it in my head. I don't really form the Kafka forms like I'm showing you, right? So here is how I think of it. Assign 6 + 9 people IDs and 6 male, 9 female identification cards to the objects. Sample space, 5 selections grouped by person rank. So what you do is I give the people rank, right? So I list basically I have person 1, person 2, person 3, all the way to person 15, 6 plus 9, yes. And then I also have male 1, male 2, male 3, woman 1, woman 2, woman 3. I code them. I give them both population ID and color ID. They are just like the balls in the previous example. And so here is my form that I will select for for the sample. So if the people IDs that were selected is 3, 7, 1, 13, and 10, that means that I will have 1, 2, 3, 4, 5. I will put them in order. So I am if I select simultaneously, I can group my presentation in order. So it will be 6 plus 9 choose 5 possibilities to fill in this form. Do you understand why it's 6 plus 9 choose 5? We dealt with this situation as a sub procedure. Good. And here is my Kafka form for the desired, to calculate the desired event. Okay. So when I have this number, I will look at this. Let's say those are the population numbers that were selected. Then I look at their female or male IDs, and I group the male IDs in order, and I group the female IDs in order. And how many possibilities are there to fill in this form? This form can be filled in 6 choose 3 possibilities. This form can be filled in 9 choose 2 possibilities. Good. So the desired probability is 6 choose 3 times 9 choose 2. And by the way, look at it. Even though multiplication is commutative, by me writing it this way, if I want to preserve the if I want to preserve the form of my numerator document, that tells me how I did the calculation. You understand? It tells me exactly how I carried out this calculation. And I imagine when I see this numerator, I right away imagine this document. And when I see this denominator, I right away imagine this document. Okay, so I did the sampling simultaneously because simultaneous and sequential sampling give the same result, but one might be more complex than the other. Are you with me, guys? And some people were asking, what is it that I mean about different sample spaces? And that will be the next issue that I will describe precisely. Are you with me? You understand how I think, yes? Develop this type of thought. It doesn't have to take as long as I did to explain it. You understand? You just do it in my head. I see the form, I imagine filling it out, and I put it in. And it really trains your imagination as well. Yes? It also helps to speak German for such things. So here is what I mean by making a clever choice, okay? So let's consider this next problem. The next problem is there are n balls in the urn. One ball is special. If we pick k balls randomly, what is the probability that the special ball was chosen? You understand? So we have n balls, and one of them is golden. One of them is a victory ball. The others are all the same. We don't care. If we pick exactly k, what's the probability that the special ball is chosen? We'll calculate it in several ways. Sure, well, and you can do that. Valeria, I'm not entirely sure. It's maybe you mistyped. It's incomplete. I need. I'm not sure what you say. CK CN. I'm not sure what it means. So, Kazi, you say K choose one. I choose. You have to understand in this procedure. I choose exactly K balls. I have to pick K, not one, but K. And then the question is, what's the probability that one of them is that desired special ball? Okay, Chabeli, you said n minus 1, choose k minus 1. Well, careful, Chabeli. Again, guys, you see? Chabeli, numerator is incorrect. Make a Kafka document. You see, guys, you refuse to make Kafka documents. You're not following bureaucratic procedures. You must, you see, it doesn't matter if you're right or wrong unless you have a document, right? That's the idea of the entire thing of bureaucracy. Without a document saying that you're right, what you are is not important. You see, you're just, oh yeah, I don't need to listen to him. I don't need to make Kafka documents. No, you will make Kafka documents here. Good. And guys, stay after class. We can do so many nice things in office hours, right? Where the camera is off. Let me know when you're ready, guys. Okay, Naomi, and I see what choices you made. Let's now solve it together. What do you say? Or are you still thinking about it? Melissa, how is it? Good or musing about it?
Like I figured out one, but then I'm still stuck at some point.
So something is, do you see, it's just, we pick out, so you can, at least if you cannot come up with the simplest solution, you can definitely come up with some solution, yes? So you just pick out K balls, one of them has to be the one we like. And yes, that's the idea. But so let's guys solve it together. What do you say? Okay, so here I'll do it through several assumptions, and then hopefully you will understand what I mean by picking the appropriate sample space. So first of all, I will assign IDs, ID 1 through N, and the N will be the ID for the special ball. Make sense? So the last ball, which you can imagine is gold, and all the others are black, is N. It has the number N on it. And so let's say I assume that selection was carried out sequentially. If selection was carried out sequentially, I can say which was the first ball picked, which was second, which was third, which was K. So that's the Kafka document for the sample space. And it's clear how many possibilities there are, right? You can have N times N minus 1 all the way times N minus K plus 1 possibilities, or simply N choose K times K factorial possibilities to fill this document, correct? N choose K because that gives you the number of ways to pick the balls times K factorial. You can actually put it in another form so you can see why it's K factorial times N choose K. So I lie a little bit, right? When I write this document, it's not automatically K factorial times N choose K. Another form will give you this possibility, right? The actual answer here will be N times N minus 1 times N minus 2 all the way times N minus K plus 1. So when I put this, it's just I'm actually counting another document here. You understand? So because why is it N choose K? N choose K means that I should have gaps between the lines, and then something else here should be the K factorial. So in fact, when I put this number here, I'm not using my Kafka document to count it, but this one is easy. Here is where I do use my my Kafka document truly for E. What? For E, it will be okay. So here is one document here. So I will put here a moment of ball end selection. Okay, and here I will put the order in which the other balls were selected. So imagine that this was the outcome. The actual outcome was first ball, then second ball was the desired ball, then second ball, then all the way to K minus 1. Understand? I just kind of picked an easy selection, right? So then how do I put it? Here I put the number 2, and here I put 1, 2, all the way to K minus 1. Understand? So this together with this information will tell me how to carry out the arrangement. Make sense? You understand how I did it, yes, guys? So it's very important, guys. You see how I think so. I actually, even when I wrote k factorial times n choose k, and I used this document, I lied. Because this is not the information that I get by using this document. Yes? But here I was very precise, right? I said exactly how I'm going to determine the counting. So here I say this is the moment in the sequence of size k where the special ball appeared. I put this moment, and here I put the relative sequence of the remaining balls. And together, this obviously will give me this information. So if I selected the k ball, there are k possibilities, correct? It's either first or second or third. There are k possibilities for that. And how many possibilities are there for this information? Well, you can say it's n minus 1 choose k minus 1 times k minus 1 factorial possibilities, even though that's not directly how I count those possibilities. Yes, the direct way to count them is that they are n minus 1 objects, and they are going to be n minus 1 times n minus 2 all the way to n, basically all the way to n minus k minus 1 plus 1. But I can just write this here. So then look what happens. So this is my probability. It's this is my numerator. This is my denominator. The k times k minus 1, it's k factorial, they cross out, and I have n minus 1 divided by k minus 1 over n choose k, some value that many of you have arrived at, already indicating that maybe this procedure is not our best. But look at it. Let's simplify this number. Let's see what is this equal to. And I can use that, I can simplify without doing any calculations. I can use some identities from chapter 1. You remember them? So I realized, well, let me multiply numerator and denominator by n. And then I can change the numerator to be k times n choose k. What is this? Because look at it, n times n minus 1 choose k minus 1 is how many ways do you choose a group, a jury out of n possible jurors of size k, and you choose the leader of the jury here, right? So I can first choose the leader and adjoin to him the other jurors, or the other members of the committee, or I can first choose the committee, and out of the committee elect the juror. So numerators here are combinatorially giving you the same value. You understand how I reason? I did not write it out. I just show you the reasoning, and then yes, and then I can cross it out. This becomes n choose k. I can cross it out. This n here survives, and the answer is k divided by n. So solution number 1 is obviously not the best solution. You already came up with a better solution, some of you, because you came to n choose n minus 1 choose k minus 1 divided by n choose k. All of you who offered me a solution came to this one, right? So you did a different sample space. Okay? Are you with me, guys? So here is where selection is carried out simultaneously. Then there are gaps here. That means that I choose k individuals. I have n choose k possibilities for the sample space, simultaneous selection. And then here I will indicate that I chose the special ball and what remaining balls I selected in order. So that would be n possibilities for so this is already taken. This box I don't need to use. It's taken. It's filled in with n all the time because I picked the nth ball, and I just need to pick remaining k minus 1 out of n minus 1 balls. You understand how this form is working? So this part is already given. I mean, I already know I picked n. The special ball is here, and there are other k minus 1 balls in the sample. Yes. Good. And so the answer is n minus 1 choose k minus 1 divided by n choose k, which is k over n. Again, slightly simpler calculation. Notice they are not the same sample space. Do you understand why they're not the same? Because the sample space here does not indicate in which order the balls appeared. There's no record of that. So it's a different sample space. But maybe you think they are kind of very similar. Let me show you a much more clever way of doing that. So imagine that that the actual selection is basically you have a pass dispenser. and the special ball is like your special candy, right? So in the pass dispenser, the n objects can be arranged in any order, but once they are arranged, then you just kind of open the pass dispenser, and you are going to shoot the first k balls or the first k candies out of the dispenser. Make sense? So selection means being in this red region of the pass dispenser. Good. So my sample space is actually going to be the position of the special ball in the dispenser. Look at it, completely different sample space. I only record the position of the special ball in the dispenser. Are you with me? So my sample space is just one box. So in this picture, the candy will be selected because it is in the third position. So I just record third position, right? Okay, so that means the selection happened. So how many possibilities for the special ball? Well, it's either in first position or second or third or fourth, or all the way to the nth position, correct? So the sample space has n possibilities. It has only n nodes. The other sample spaces have many more nodes, right? And then you realize that there is no preference. You agree? If the universe is indifferent, then there is no position that is preferred to another position. Okay, the ball is equally likely to be first, second, third, fourth, k, and so on. Good. So then, how many possibilities are there to be selected? So E, the outcome is that the place is so that the special ball is selected. Only k possibilities, one of those possibilities. Okay, so the answer is immediately k divided by n. Do you see how much faster I solve this problem? Do you understand, guys, what I might now? Do you understand what's the difference between sample spaces? That you are not forced, you're not confined to one sample space. You just have to kind of reason and be very careful, of course. Okay, there are some jumps, of course, of intuition that I made, right? So the actual sample space seems to be different, because if I imagine the actual situation, I actually imagine selecting all the other balls. Yes, but this information based on, again, on this idea that there is no preference to the placement of the special ball, that I can just right away see the answer. You see, and the reason the solution is the same is because of two combinatorial problems, right? We are solving here a very different combinatorial problems than in previous exercises. It's that 3 divided by 6 is the same as 1 divided by 2. Make sense? So that means that if you pick another different sample space, you can still calculate the right probability. Good. Is this thing about sample spaces clear to you guys? Right? Yes, if you understood that you can, you're not forced to imagine just one specific sample space. You can switch from one to another. And you need Kafka forms. Is that clear? Why? You already are making mistakes on very simple questions. You need to imagine what you're counting. Good. Let's try this problem. Poker hand is equal to 5 cards. And if cards have distinct consecutive values and are not of the same suit, we say that the hand is a straight. What is the probability that one is dealt a straight? Assume that all possible hands are equally likely. Just before I continue, I never play cards, but do you know what cards are, what they look like? How many cards do you have in total? 52 cards. And how many suits do you have? 4 suits. And so you understand? So there are 13 different cards within one suit. Good. Now try to figure out what's the probability of being dealt a straight in poker. Kafka document. So you see, I do not play cards, so I'll tell you what was my assumption. It might be that other people think of it slightly different sometimes, right? So I'll show you what was my assumption. Important thing is that you imagine something and then you count the thing that you imagine. Erica, one small thing, the cards cannot be of the same suit. Exactly, Erica. Yep. Again, guys, Kafka document. I want to see that you understand how to solve this problem procedurally. If you have intuition and can do it fast, that's great. Ready? All right. So first of all, I assign every card a population ID 1 through 52. So each card has a number associated with it, attached to it, 1 through 52. So if I select without order, in other words, simultaneous sampling, then there are 52, choose 5 entries in my sample space document. Yes, where I enter in order. You see, when I put this, when I put the values that I selected in their population order. Good. That's how I will search for the sample space. That's how I know there are 52, choose 5. And we developed mechanisms for that from previous example. Now let me tell you this. When you think of your objects, think about how you model them. So a card is going to be having a front number and a back number. The back number is its suit number. You understand? So for example, ace of hearts might be 1 and 1. So the front number has 13 possibilities, right? So there, for each suit, there are 13 different cards, which I imagine listing in particular in order associated with their ranking, right? So there is, I'm not sure, ace maybe it's 1, then 2 is 2, then 3 is 3, and you just give them order. Okay, I do not know what card orders are, but a straight doesn't matter. A straight is this ranking based on the card's order. And here is my Kafka document or Kafka protocol. So if it's a sequence, if it's a sequence in order, I will write the first of the consecutive numbers that appears here. And then once this first number is written, the next numbers of the straight are immediately implied. Do you agree? So let's say if I know that my first card was 1, maybe 1 is ace. I'm not sure, right? And then the next has to be 2, 3, 4, and 5. So here I put the smallest of the consecutive numbers. And here I put the suit for those cards. So first card can be any of 4 suits. Next card can be any of 4 suits. Next, any of 4. So there are any of 4 to the power of 5 suits. That's the possibility here. Agreed? But the reason I subtract 4 is because imagine that I put here numbers 1, 1, 1, 1, right? That means they're all from suit 1. Maybe suit 1 is hearts. Or maybe it's 2, 2, 2, 2, right? So there are 4 possibilities. It's just taking a number and repeating it. 1, 2, 3, 4. So I subtract those possibilities. And that will allow me to count only the situation where they are not all of the same suit. I subtracted numbers that correspond to all the same suit. You see, guys? So now how many ways are there to fill in the first entry? Look at it. What is the last number that I can put there? The last number is 13 minus 5 plus 1. You understand why I do 13 minus 5 plus 1? No? Why minus 5? There are 5 cards, right? So the first, I'm asking what's the biggest first number I can have? Clearly it cannot be 13. Clearly it cannot be 12, right? So what is the biggest number that I can put here for the to be the smallest consecutive? So I take 13. I need to go back from 13 5 units. So it's 13 minus 5. But 13 minus 5, the 5 that I subtracted, that includes all the consecutives. So plus 1 gets me to the first consecutive. You understand? 13 minus 5 means coming below the first consecutive. Plus 1 returning to the first consecutive. Does it make sense what I'm saying, guys? Just basic algebra, but does it make sense to everybody? You see why I basically what I do is from the biggest number, I subtract the size of the group and add 1 to be the first member of the most extreme group. Good. So it's 13 minus 5 plus 1 possible entries here, because it could be 1, 2, 3, etc. What's the biggest number it can be? 13 minus 5 plus 1 is the biggest first consecutive number that I can have here. You understand? You see with my hands, subtract 5, you went right before the last, the last group that we can have here. plus 1 will get you to the first number. Good? So this is my answer. It could be that the actual straight, there are some other things that I don't know, because I think this problem I borrowed from your textbook, and I think they put 10 instead of 9. Now, the reason they put 10, possibly, well, I'm not sure how they do the counting. You understand? I mean, that means that perhaps what they consider consecutive is not entirely the way I understand consecutive. Maybe the ace of spades might be considered both the biggest value and the smallest value. It might be considered as 1 or as, that's one way that it can happen, for example, right? But that doesn't matter to us, right? That's the probability I calculated. It's 9 times etc. Good? The explanation makes sense? So, I don't know. Do you want to solve one more question, or do you want to retire to office hours? It's already 6:50. The question, okay. Sequential, just unnecessary. You would have things canceling in numerator and denominator. It's wasting your time. Okay. So do you want one more question, or do you want to retire to office hours? It's not a combinatorial question. One more. Okay. So this is the next question. It has actually two parts, part A and part B. If all the 52 choose 5 poker hands are equally likely, what is the probability of getting one pair? You understand what one pair is? Means that you get 2 front identical numbers and all the other numbers are different. And then the second part is 2 pairs. When you solve those questions, I want to see a Kafka, well, I hope I can, we'll see it on the exam, Kafka document. No, a pair cannot be of the same suit, Melissa. So a pair means that front value and second front value are the same. So for example, I might have king of hearts and king of spades. That's a pair. And all the other cards are not kings and not equal to one another. Make sense, Melissa? You let me know when you're ready, correct? There is Naomi, so you have 13 minus 1, choose 3. 1 choose 3 is 0, it's meaningless. You mean maybe 3 choose 1, or I'm not sure what is that. And 4 cubed. 13 choose minus 12, choose 3. Okay, I think I know what you're trying to say now. Document is important, guys. And then solve B if you finished A. Again, guys, the hint is when a particular outcome occurs, the desirable outcome, then you want to know how do you file it, right? What sort of desirable outcome did you have? Here it comes in, it happens to be 2 pairs. How do you file it as? How do you report the 2 pairs that actually happen, if they happen? Let's solve A together. Unless, of course, guys, let me know. Should I wait longer before I solve? I just worry you will run out of patience. Let me know if you want to continue working on it, or should I go ahead with solution to A? type W if you want me to wait, and type G if you want me to go. In other words, solve it. Okay, so a lot of G's. I guess I will go ahead and solve it. So I am dealing with simultaneous 5-card selections here. So it's clear to me that sample space is 52 choose 5, yes? Then here is my document. If I get exactly 2 pairs, then I can give the information as follows. So first, if I have 2 pairs, what was the number on the pairs? Okay, so pair number, and then what are the suits? Pair suit, right? So I will, the suits are listed 1 through 4, correct? So I will file the suits as first the smallest suit, second biggest suit. So this information, so those 3 boxes, they give me information about the pair, complete information. Do you agree? So for example, if the number here is 1 and here is 1, 2, that means I got ace twice. 1 is, let's say, ace. I got ace twice, and 1 suit was 1 hearts and 2 diamonds. Okay, that depends on how you decide to label the suit color. So suit color is associated with the number. You could have given a code. So let's say 1 through 13. There is a translation. 1 through 13 tells you what's the card. 1 through 4 tells you what's the suit. Good. So this tells you the information on the cards. Now, what is the information about the remaining pairs, the remaining front numbers? So there are going to be, I have another 12 numbers available to me. And out of those 12 numbers, I need to choose 3 numbers. I will list those numbers in order from smallest to largest. They cannot be the same number, yes? Because if they're the same number twice, if one number appears twice, then I have more than 1 pair. So here I put the remaining 3 numbers, and here I have the suits. 1 suit, 2nd suit, 3rd suit, right? This is the suit of the smallest number, suit of the middle number, and suit of the largest number. You see that this information, if I file it, will give me full information about the cards that I selected. Is that clear? So the answer is then 13 choose 1, because there are 13 possibilities here, and 4 choose 2, because out of 4 suits I need to choose 2 suits, which I will arrange in order. That's information about the pair. Now 12 choose 3 is information about the front number on the remaining cards. 4 cubed means that it's 4 possibilities for first card, 4 for the next, 4 for the last. Yes, so that is 13 choose 1, 4 choose 2, 12 choose 3, 4 cubed. And that's my numerator. And since I have the denominator here, I can then use a calculator. The probability is approximately 42% to have 1 pair. So it's 42% likely to have 1 pair. Okay, great, good. So except okay, good. So that was for part A. Do you want to go through part B, or do you want to call it a day and go to office hours? Okay, Naomi, take care. So the remaining people want to discuss, I'm assuming you want to discuss. Okay. You can rest a little bit and then return to office hours if you want, right? So these guys, let me know so that I don't quit the session if you would like to continue to office hours. Okay. There are many problems you should be solving. We can finish the problem B if you want, guys, right? So I will finish problem B if you stay with me. If you want to go, then you leave. So guys, so oh, Shotaro, that's not good. You should have stayed, but okay. Oh, Melissa, we'll cover this problem yet again on Wednesday. I will talk about it again. But you see, so I just received another message from a certain rodent, and so what you might say is, you see, I really want to see a document that once I read the information in the document, then I know exactly what's the outcome, right? So even if the answer is correct in your mind, I want to see that you can actually produce documents. Should we go over problem B now? Okay. Yes, let's go over problem B. This one is a bit more tricky. Okay. Again, for problem B, sample space is the same, but here is how I will do what I will do with my cards. My numerator document is different. You see, this is the numerator document I have in my mind. So first is values on the pairs. Okay. So it will be 13, choose 2. Once I choose the numbers, I arrange them in order from smallest to largest. Good. And next, each of those numbers corresponds to 2 suits. Yes. So I will choose 2 suits for the smallest numbers, suits for small, and 2 suits for large. Yes. 13, choose 2. And what are and then basically those boxes here that I'm circling will explain to you what sorts of pairs did you select, because you need front number and back number. So it's 13, choose 2. 4, choose 2 possibilities. So once I choose 2 suit values, I arrange them from smallest to largest. I do the same for the larger denomination. And now I have 13, choose 2 times 4, choose 2, 4, choose 2. And then remaining cards, look at it. I cannot select any of the cards that I have here. How many cards did I remove? Actually, be careful. Not only so they are. This number repeats itself 4 times. This number that I selected here repeats itself 4 times. So there are 8 cards that are not accessible to me. Right? There are 52 cards. There are 4 cards of this number, 4 cards of this number. Altogether, 8 cards not accessible to me. So I can just select it as 52 minus 1, choose 1. You can actually construct it differently. You can do it. You can do a different form. Maybe you would like to say, I cannot choose those values, so there are 11, choose 1. 11, choose 1 denominations available multiplied by 4 possibilities. So this is the same as 11, choose 1 times 4. Good. Let's see what is it that we have here. Does it make sense, guys? Again, right? I hope that you are writing. You understand how do you know if you wrote the right document? If I fill it out, and you can imagine exactly how it is filled out, I will be able to know what is the outcome. And every outcome can be recorded in this way so that you can reconstruct it. If you can do that, then you know that your answer cannot be wrong. Good. Okay. So yes, so that is again for part B is correct. Yes, but remember that the boxes that I see here kind of, you know, I mean, there's also the number boxes. The boxes are not enough for a full bureaucratic document. And when you work in school, you know it's only bureaucracy. That's all it is. Okay, so that will be the lesson for today. We can talk about more problems in office hours where we can try to experiment with this platform here, if you want to see how it works. Hopefully it works this time. Hopes it works well. All right, I'm stopping the recording.